here. So we have Kirsten Zickfeld, and I don't know your exact title, is a distinguished professor of climate science at Simon Fraser University. Within the CanCore project, she is coordinating the activity examining the environmental equivalence of CDR deployment scenarios, along with me.
Okay.
Kirsten, take it away.
Thanks for the introduction.
So and forward, back.
Okay, and I need my talk. Okay,
there you go.
Okay, good. All right. Good. So thanks for the full introduction, and good afternoon, everyone. So we've talked a lot of CDR, and ultimately the reason we're doing this is because we want to reduce the concentration of carbon dioxide in the atmosphere, and we want to mitigate warming. And so what I'm going to do here is talk a little bit how removing carbon dioxide from the atmosphere affects the actual carbon cycle and also affects temperature. So I'm not going to talk about other climate science metrics to make it easier. So generally I'll talk about the effects on the carbon cycle, on temperature. We'll see that there are not only the effect of the carbon dioxide that we're removing, but also from other effects. So Daniel mentioned that earlier in the introduction, because there are co-emissions both in the fossil fuel burning space, but also in the CDR space. And for these reasons, when we talk about carbon neutrality, we may not necessarily achieve climate neutrality. So I'm going to unpack that a little bit, and also the implications for net zero scenarios. Okay, so let's talk about the carbon cycle a little bit. So when we emit a ton of carbon dioxide into the atmosphere, only about, so this is indicated by, so G here means that the geologic reservoir, so we're taking carbon out of the geologic reservoir, we're putting that into the atmosphere. And when we do this, then that carbon repartitions into the land and into the ocean, which are those carbon sinks, right? So that only about half of that carbon actually remains in the atmosphere. So the ocean and the land do us a huge service because they actually mop up half of the emissions that we put into the atmosphere. So now what if we remove a ton of carbon dioxide? So this is shown at the bottom. So now what we do is either we remove carbon dioxide directly from the atmosphere via DAC, or through land-based methods as in BECCS. And so now what's happening is essentially the same redistribution mechanism, but in reverse, right? So now we're removing carbon dioxide from the atmosphere. So now what the land and the ocean do is they return some of that carbon into the atmosphere. So what this means is that if we remove sort of net, if we remove 1 ton, only about half of that will remain out of the atmosphere. So when we're talking, Kazra gave introduced this sort of nicely because he defined these two roles for CDR. So when we think about CDR as an offset to emissions, and we're still in a state of the systems where emissions are net positive, so we're emitting more than we're removing, then we go with the upper picture. So we're still so land and ocean will take up carbon dioxide. But let's say once we go into the space where there is a net negative emission, so we're removing more than we're actually putting into the atmosphere, then we'll see on a global level those sink returning carbon dioxide back into the atmosphere. And so we can quantify this by running global climate models. So these are experiments with these very complex Earth system models. So there's a whole bunch of them. So this is a figure from the IPCC report. So the experiments that we did with these models is we instantaneously removed 100 gigatons of carbon. That's a huge amount. In Earth system models, we need a very large signal because we have interannual variability, right? So as we know, weather varies from year to year. So we need a signal that is actually larger than that interannual variability. And so we need at least 100 gigatons in order to be able to detect a signal. And so here the experiment, so this is net removal from the atmosphere, but I want to emphasize that this is also true, let's say, in a situation where we have a business as usual trajectory, and from that we do remove carbon, and then we look at the difference between our business as usual plus CDR relative to the business as usual trajectory. So here the experiments are set up at net removal, but this would also be true and if we're comparing the effect of CDR versus a trajectory that does not include CDR. And so what we see is at the top, what you see is that when you remove that carbon instantaneously, your CO2 in the your concentration of carbon dioxide in the atmosphere declines very rapidly, but then it comes back. So this is the so-called rebound effect. And in the middle and at the bottom, you see that that carbon that is now re-added to the atmosphere comes out of the land and the ocean. And so then you can ask, well, how much is then replaced? And so here these models show that there's a little bit of uncertainty if you do the math. So in the upper model, you see that the concentration almost rebounds to its initial value. So there the effect is 15%, whereas in other models it's around 35 to 40%. Okay. So then we can calculate a removal efficiency, and we can ask, or effectiveness, and we can ask of the CO2 that we actually remove out of the atmosphere, how much remains out, right? And that is our removal effectiveness. And then we can ask, well, does this depend on how much we remove? Does it remove from what state? Does it depend on what state we remove it from? And so again, with simulations with Earth system model, we find that first of all, this removal effectiveness depends a little bit on how much we remove, not so much, but it depends quite strongly on the state from which we remove it. And I would say sort of one interesting result is that actually this effectiveness, so the amount of carbon that stays out of the atmosphere after we remove it, does decrease with decreasing initial atmospheric CO2 concentration. So which means that if we do this when CO2 concentrations have already come down, it's actually harder to do than when CO2 concentrations are higher, which especially when we think about net zero pathways is sort of not so good news. Okay, good. So this is sort of concentration of carbon dioxide in the atmosphere, but ultimately what we're interested in is temperature. So we want to know when we remove carbon, how much cooling do we actually get? And again, Kazra's presentation earlier introduced us to this idea that there's this proportional relationship between warming and cumulative carbon emissions into the atmosphere, and that same relationship holds more or less also for cooling. So we can say that the amount of cooling that we get per unit of carbon removed from the atmosphere is roughly proportional to the amount of carbon removal. Okay, so that gives us a nice metric, because then we can, once we know the amount of carbon that we remove from the atmosphere, if we know sort of the slope of that relationship, which we call the transient climate response to removals, then we can calculate what the temperature benefit is from that. So this is as far as carbon goes, but as I hinted at earlier, we also need to think about the other effects in which both emissions into the atmosphere or removals out of the atmosphere affect climate. So first of all, both emissions, but also some CDR methods go along with emissions of other greenhouse gases into the atmosphere. So for example, if we think about bioenergy plantation, we may fertilize some of them, which then results in emissions of nitrous oxide into the atmosphere. Or when we think about peatland restoration, that comes with additional methane emissions. CDR methods also emit aerosols. So aerosols are particulates. They're not gases. So for example, when we plant tree, they may emit volatile organic compounds, or VOCs, which then interact with clouds and so on and have an effect on climate. And then with approaches that modify the surface of the earth. So again, this could be planting trees, but it could also be BECCS if bioenergy replaces some other type of land use, or even very large scale DACs if the footprint is very large. That influences the fluxes of energy at the Earth's surface. So things like the reflectivity or the albedo, the evapotranspiration, so the extent to which plants can access water and transpire that into the atmosphere. And so this here is a figure from the IPCC report, which summarizes some of these non-carbon dioxide effects here within this blue box. Here, so this is a complex figure with a lot of details. What you find in the vertical, these are the different CDR methods. They're ordered by the time scale of carbon storage. So we have the biological ones on top, where the time scale is decades to centuries, to the more geologic approaches at the bottom. And then what I want you to look at is those squares within the blue frame. And what you see there is a number of biogeochemical effects. So these are the non-CO2 greenhouse gas emissions and aerosol emissions, but also these biophysical effects, which refer to these changes in the surface energy balance. And for example, if you look at let's say at BECCS, which is the second last from the bottom. So you see some of these purple boxes, which is an indication that there are additional effects through emissions of non-CO2 greenhouse gases, but also potentially some effects on the surface energy balance. Okay, good. So then sort of why does this all matter? So often when we think about offsetting, we think that balancing an additional ton of carbon emitted into the atmosphere with a ton of removal is the same thing as not emitting that ton of carbon, right? So that's kind of this idea behind the carbon neutrality, that instead of not emitting, we balance the emission with the removal, and then we end up in the same state. But again, this is only in a very idealized way, because again, the emission system, so when we cut down forests, or when we burn coal or natural gas, we emit carbon dioxide into the atmosphere, but also suite of co-emissions, so non-CO2 greenhouse gases, but also aerosols, right? But then on the other hand, the solutions to then sequester that carbon from the atmosphere and then store it in different reservoirs have their own non-CO2 greenhouse gas co-emissions and also effects on the surface energy balance, so that perhaps sort of maybe if in theory we achieve, so that we can balance a certain amount of emissions with a certain amount of removals, because of these non-equivalencies between emissions of removals, we may balance the emission, but not necessarily the climate impact. Okay, so this is why when we think about the climate effects, we need to think beyond carbon. So to demonstrate this, we did an experiment, again with an Earth system model. So this is from from a PhD student in my group. So here we chose reforestation. So the extent is shown on the left-hand map. So what we did is we reversed historical deforestation. So essentially, we restored the state of forests from pre-industrial times. And you see by these green areas where additional forest grows. Then what we did is we calculated how much carbon dioxide do these forests sequester. And so this is shown in the middle. So that's the amount of CO2 that these forests sequester per year over about a century. And then in our model experiment, what we did is we quantified an additional amount of fossil fuel emissions, which is exactly the same as the amount that is removed by reforestation. So in a way, this would be sort of a net zero state, right? So that we emit additional carbon into the atmosphere. We balance that by forestation-based removal. And so let's say through our conventional understanding, we would think, okay, good, so this is net zero. So in a way, this is climate neutral. And what we find that it's actually not. So we find that maybe I should go back to show what the reference case is, right? Sort of then what we do is we compare the result of this net zero scenario where we compensate emissions with removals with the baseline, so that's the red line here on the right-hand side, which is a true zero baseline. Okay, so this is an idealized scenario where we actually, instead of going to net zero, we go to real zero. So we go to zero emissions, and then we ask, is the climate outcome actually the same? And here, by comparing the green and the red, you see that that's actually not the case. So we get a higher atmospheric carbon dioxide concentration. So just in a nutshell, this is because planting trees warms the surface air in some regions, which then affects fluxes at the surface, resulting in emissions of carbon from the land. And then in addition to that, so this is on the right-hand side, this higher atmospheric CO2 concentration is then also amplified by what are called these biogeophysical effects, which are the effects on the surface energy balance. So forests are darker than grasslands or crop regions. Also, their roots are shallower, so they're not able to access water in the soil as deeply. And so all of these effects affect temperature as well. And I would say, so this is a sort of quite a significant effect. So we see that by the end of the century, we end up with 0.1 and even a little bit more warming than if we did not emit those additional emissions and offset them with reforestation-based removals. So this is one model. So this is so sort of next step would be how robust is it? All of these effects are highly uncertain. So if you repeat that with the different Earth system model, you most certainly get out different numbers. But sort of qualitatively, this result is quite robust. That if you compare net zero scenario with the true zero scenario from an Earth system perspective, you cannot expect them to be equivalent. So then, very quick summary. So only a fraction of the CO2 that we remove by CDR remains out of the atmosphere. So this, as long as we're in this phase where we offset emissions with removals and we're in a net positive emission state, this doesn't matter, but it becomes important when we transition to net negative emissions. Then the amount of carbon dioxide that remains out of the atmosphere, which I introduced as this measure of effectiveness, is slightly sensitive to how much we remove, but is more strongly sensitive to the state from which we remove the carbon. The net effect of removal on surface air temperature is not only determined by the CO2 that we remove, but also by these non-CO2 effects. And this is why we need to consider these Earth system effects in net zero scenarios that balance additional emissions with CDR. So I leave it here, and I'm happy to answer any questions or move to the discussion. Thank you.